Here we continue our discussion of our discussion on how stress looks like in a fluid and the forces which are imposed within a continuum, which is not a solid but a fluid. So we started by discussing fluids at rest, and in the fluids at rest we discussed that the stress tensor should be an isotropic tensor where the constant really is the pressure. And what we discussed is if we're thinking about a piece of the material of a fluid which is under normal, which is under stress, right, in static equilibrium, then the stresses from all directions have to be equal, otherwise the fluid would flow. Also, this gives you an indication that when the fluid is being compressed isotropically or pulled isotropically, that really what the pressure represents is a stress which develops inside of a fluid in order to prevent, and that's especially true for an incompressible fluid, in order to prevent a change in volume. And now we're going to discuss stress in the fluid that moves, and what we'll see is that when we discuss fluid in motion, so U is no longer equal to 0, the flow is no longer in static equilibrium, so this is no longer holds, we have to add another term to the stress tensor. So we discuss stress in a moving fluid. So far in our discussion of how forces are applied within the continuum, we've discussed that we have to represent what the object that we need is a stress field, right? So this is our stress tensor as a function of x and t. We found that it has an isotropic component which corresponds to the pressure. And now if we have a flow which is moving, then we have another component which I'm going to call tau, and this tau should be a function of the flow field, so it should be a function of u. But really we've discussed, and if you can find this discussion in the mathematical videos, that a velocity field locally can be split into a translation. I should actually say, so the velocity field really represents the motion of the continuum. And if you think about the motion of a continuum, well, and that is true for the velocity field, it can be represented by a translation plus a rotation. And translation and rotation is what you would have if you had a non-deformable solid, right? But of course, the velocity field represents the motion of the continuum. So we have translation plus rotation. We also have deformation. And the deformation in the velocity field is represented by the rate of strain tensor. And so if you think about the stress inside of a fluid, stress inside of a fluid should not depend on the motion, which is a translation. If you think about something which is translating, there shouldn't necessarily be stress or forces applied inside of the continuum. If you have a solid body rotation, neither. You don't have any deformation, and therefore what we expect is that our stress here will only be a function of the deformation, and therefore mathematically it will only be a function of the part of the motion, the part of the velocity field which represent deformation, which is the rate of strain tensor. And the rate of strain tensor is equal to 1/2. Let me write the rate of strain tensor at a certain location and at a certain time, because it is a field. So at every single point in the continuum, we can define this rate of strain tensor, and it is equal to the gradient of the vector field u plus plus the transpose. So this is the matrix when you flip it along the diagonal of the gradient of u. So the question is, how does our stress tensor here, tau, depend on the rate of strain tensor? This is when we essentially put into really our system that we are looking at the fluid and not at a solid. This relationship between our rate of deformation and tau is what, or it could also be some in solid mechanics, is the relationship between the strain tensor and tau is called a constitutive relation. Before, what we did when we derived Cauchy momentum equation, we were just imposing Newton's second law. We were not saying anything about the particular material we were looking at, but when you start describing the relationship between deformation, or between rate of deformation and stress, this is really when you start describing what kind of material, what kind of properties does the material have that I am considering. And so for a fluid to think about how do those two relate, you have to use your intuition, and you already have some experience with fluids. So if you think about the simple experiment that we saw today, last week, when you simply shear a sample, say we have two plates of surface S, and in between we have our fluid sample, and we shear by imposing a velocity on the top plate equal to u. Let's say that this gap width here is h, and that the fluid that we have inside is a fluid of density rho and viscosity mu. Now if I ask you what is the force exerted by the top plate on the bottom plate, then from a scaling you would say, okay, so F, this force, is going to be roughly equal to the stress which is imposed on the surface S, so that would be a stress times the surface S. And what is a scaling for this stress? Well, if you have a viscous forces, then your stress, you can reason in terms of dimensions, that would scale with mu, we've seen that before, u divided by h times s, right? Another way of one way to get to this scaling is to think about the dimensions. So this needs to be a force, so this needs to be a stress, so it needs to be kilograms per meter per second minus 2. When we think about the viscosity, that's the only thing that we have that has kilograms inside, so kilograms meters minus 1 second minus 1. You need a second minus 2, so if you multiply by a velocity u, you'll get your second minus 2. Those are now meters second minus 1. I have kilograms now second minus 2, and I need to divide by a length scale, and the only length scale that I have is h. So if I divide by h, I get mu u divided by h times s. So this is how you can get to a force by scaling. And of course, you see that this really corresponds to the double integral over our surface S of a shear stress, which we could write as mu partial u partial y ds. Okay, so this is something which you may have seen before, right? That the stress, a shear stress, a viscous shear stress, can be expressed as mu times the rate of shear, partial u partial y. But then if you think about that, so this is my shear stress, let me call it tau, is equal to mu partial u partial y. What you're essentially saying here is that your stress is equal to a constant times your rate of strain, right? And so you're saying that the stress is linear in your rate of deformation, right? So when you say that, this is very much equivalent, right? This is along the same lines as saying, well, if this is what I can think about physically, then mathematically, one would expect that this relationship here is a linear relationship, and therefore, one can think about a constitutive law for a fluid where the rate of strain, where the stress tensor is linear in the strain rate tensor. And that is actually the definition for a very broad range of fluids, which are called Newtonian fluids, and which are the fluids that you have the most experience with: water, air, oil, all of these are Newtonian fluid. So a Newtonian fluid is a fluid where we have a linear relation between the stress and the rate of shear. Sorry, rate of strain to be more exact, to be more general. When we have this, we have a Newtonian fluid. And that is a general definition for a Newtonian fluid. So a fluid is Newtonian when the when the stress tensor is linear in the strain rate tensor. So what does this mean? That we have such a linear relationship? Well, think about one single component of the stress tensor. Let's say, for instance, the normal stress in the x direction, tau xx. To say that this stress tensor is linear in the rate of strain tensor would mean that we can write at every single point this normal stress as an alpha times this component of the rate of strain tensor. This actually would be equal to partial u partial x plus, for example, beta exy, and this would be equal to 1/2 of partial u partial y plus partial v partial x plus gamma ex z, and that would be equal to 1/2 of partial u partial z plus partial w partial x plus delta eyx, and so on. So I have I have a matrix. E is a 9×9 matrix, so I could write Txx, so this normal stress, as a linear combination of the 9 elements within the matrix of the strain rate tensor. And we could write this not just for Txx, but for all of the 9 components of our stress tensor. So in principle, this linear relationship between the stress tensor and the rate of strain tensor would comprise 9 times 9 constant. Here I have alpha, beta, gamma, delta. I would have 9 constant for Txx, 9 constant for tau xy, and therefore in principle it should depend on 9 times 9 equals 81 material properties. So those will be constants which correspond to material properties. Okay, but luckily you don't need 81 material constant, because that would be a nightmare for an experimentalist. Now, if this relationship really depended on 81 material properties, then yeah, you would have to devise at least 81 different experiments to characterize the response of the stress response of a flow to a deformation. So that luckily is not the case. And that is because of several reasons. First reason is because we've discussed this tensor here has to be symmetric, right? Because of the conservation of angular momentum. And this here is a symmetric tensor. So each of these only have 6 independent entries, and the one on the diagonal, plus you take either the upper or the lower one, but in total you only have 6 components independent, and therefore 6 by 6, not 9 by 9, and 6 by 6 is equal to 36. In reality we have only 36 because both E and tau are symmetric. But then in addition, what we can say is also that the fluid is isotropic. It's not necessarily true for all fluids, so we're making an assumption here, but we'll assume that a Newtonian fluid is isotropic. Hold on though, maybe this is not true for all Newtonian fluids, but we are assuming that everything is isotropic here, so the fluid doesn't have a particular direction that it likes. It does not have a direction for which it's easier to shear than another. In principle, the fluid is the same in all directions. When something is the same in all directions, we say that this is isotropic. Well, if you add this assumption, so we have a symmetric tensor which is linear in another symmetric tensor and everything is isotropic, then mathematically, we're not going to show that, but mathematically you can show that the only linear relationship between tau and E can only be the following. Tau is equal to, and this relation will only depend on two material properties, one which I will call K and the other one which I will call mu. So mu, you can imagine that this is going to be the dynamic viscosity, which we've discussed before. So K minus 2/3 of mu times the divergence of U. This is a scalar, so this here is still a scalar times the identity matrix plus 2 mu times the rate of strain tensor. And so this is general for a Newtonian fluid. That is the expression, the general expression for the stress tensor. This mu is called the dynamic viscosity, and K is called the bulk viscosity. Note that here the divergence of U, you know what the divergence of U is. It is partial U partial X, but partial U partial X is also the component on the first row, first column of your strain tensor, plus EYY plus EZZ. This here is partial U partial X. This thing is partial U partial Y, and this here is partial U partial Z. Maybe I should write this here. Recall here that E is equal to 1/2 gradient of U plus the transport of the gradient of U. So if I write all of the components, E is equal to the following matrix: partial U partial X, 1/2 of partial U partial Y plus partial V partial X, and here 1/2 of partial U partial Z plus partial W partial X. All right, this is an expression for the rate of strain tensor. And this is only valid in Cartesian coordinates. If ever you needed the rate of strain tensor in polar or in cylindrical or in spherical coordinate, then you would have to look inside of your Kundu book. Right, so just note that the divergence of U is equal to here this sum, which is, if you remember your definition, this is the trace of the tensor E. So this is the trace of E.